Hello. Yes. So good evening, everyone. Okay. So good evening, everyone, and welcome to all of you for today's fourth session on chemical engineering thermodynamics. This is my short introduction that I am currently Prime Minister's Research Fellow at Department of Chemical Engineering at IIT Bombay, and we are basically working on molecular simulations and statistical thermodynamics. We are working on chemicals from biomass and studying their vapor liquid equilibria and reaction equilibria. And I have completed my BTech from SVNIT Surat in 2019. Then I joined Reliance Industries Limited at Jamnagar. Then I completed my masters from IIT Kharagpur, and currently I am pursuing my PhD from IIT Bombay. So this was about me. So in let's first go through some what we studied. So in class 2, we studied the combined first and second of thermodynamics, that says that du is equal to TdS minus PdV. Further, we found out the conditions for spontaneity, that is for constant SV system, U should be less than equal to 0. Constant S and P system, DH should be less than equal to 0. Constant VT system, DA should be less than equal to 0, and constant TP system, DG should be less than equal to 0. Further, if you remember these equations, we derived that du is equal to TdS minus PdV. This is combined first and second law of thermodynamics. Then we derived dH is equal to TdS plus VdP. Further, we derived dA is equal to minus PdV minus SdT. And at the end, we derived dG is equal to VdP minus SdT. And dG, the Gibbs free energy, is very important term because dG is estimated at constant temperature and pressure, and that is most practical in terms of most practical applications. That if you see in industry, generally temperature and pressure are kept constant. So DG is very important in terms of applications. Then we looked at Maxwell relations. So Maxwell relations basically told us how can we relate some non-measurable quantities with measurable quantities. So we had four equations, and for all those four equations, we derived this Maxwell relations. Further, we found out these two equations, and these are going to be very useful, particularly for today's class. So we found out that yes, this dH is CPdt plus V minus T del V del T at constant pressure, dP. This is one equation that we derived. And these two equations, that ds is Cv by T dt plus del P del T at constant volume dV, and at PT conditions ds is Cp by T dt minus del V del T at constant pressure dP. So what was very important for us to know, that for ideal gas, when the gas was ideal, so these two terms del P del T at constant volume and del V del T at constant pressure, this both term went to zero. So for ideal gas, it was just ds is Cp by T dt, and here it was Cv. No, not for ideal gas, sorry. These U energy terms, when we were calculating for ideal gas, so this term was specifically P by T, and for ideal gas du was CVDT, and similarly dH was CPDT. Here it will not be like this. For here it will depend on what kind of, if it is ideal gas, then P by del T we will find and we will estimate. Okay, so from here we learned that we really need to know what is the PVT behavior for real gas, because for ideal gas this term is not any significance. So from this story we went ahead, and in last lecture we go through some what is it called, some PV diagram and PT diagram, and from there we went to van der Waals equation of state, that is cubic equation of state. Three types of equations: van der Waals equation of state, Peng-Robinson equation of state, SRK equation of state, RK equation of state. Those kind of equation of states we studied in the last class, and we found out that ideal gas molecules, they don't interact with each other, and volume of molecule occupied is very less compared to, or it is negligible compared to the system volume. So there's these two assumptions were for ideal gas, and when we went from ideal gas to real gas in case of van der Waals equation of state, so we tried to incorporate those two A and B terms. Those were taking consideration. A was taking consideration of interactions, intermolecular interactions, and B was taking care of size of the molecule occupied by one molecule. So from this van der Waals equation of state we used, and we found out the constants A and B for van der Waals equation of state. So A came out as 27 by 64 R square TC square by PC, and B came out as RTC by 8PC. So if we find ZC value, critical compressibility factor, so that came out as 0.375. So that is far from what is there in reality. So if we see the what are the values at reality for critical compressibility factor, so we need to look at this chart. Yeah, this chart. So you see ZC is 0.27, 0.28, nothing less than, everything generally less than zero point 0.3. 0.286 for methane, 0.279 for ethane, 0.276 for propane. So we basically say that van der Waals equation of state is not able to correctly capture the real behavior. Then from van der Waals we went to Redlich-Kwong equation of state, and for that equation of state ZC came out as 0.333, and Peng-Robinson equation of state ZC came out as 0.3074. So like that we tried to study the real behavior of real gases. Then we went to reduced properties. So what is reduced property? Property is defined as any property divided by its critical property. Let's say I want to define reduced temperature. So that is defined as reduced temperature is actual temperature of system divided by its critical temperature. And we looked at the benefit with dealing with this kind of reduced equation of state, or two parameter law of corresponding state. From here we know that these predictions are within 5% for polar and slightly polar gases, and large deviations are for highly polar gases. So there is something we are missing from this two parameter corresponding state of theory. So from there we went to 2 to 3 parameter, and we included one additional term that is called omega eccentric factor. And for simple fluids like argon, krypton, xenon, so eccentric factor is 0. So if we plot, so eccentric factor is defined as nothing but -1 minus log 10 PR set at TR is equal to 0.7. So when TR is 0.7, we are calculating log PR set, and we are then using this formula. So it is just deviation, and omega is basically giving the idea of sphericity of the molecule. Okay, so this we studied. Then we studied the virial equation of state in two terms: Leiden form, that was pressure explicit form, and Berlin form, that is Leiden form, that is volume explicit form, and pressure form, that is Berlin form, that is pressure explicit form. So from here we learned about Boyle's temperature, that at very low temperature B is negative, and at temperature at which B is equal to 0, so attractive and repulsive forces are exactly opposite to each other, and that B is called the Boyle's temperature, and Boyle's temperature gases tends to behave ideally. Okay, and then we studied this residue property or departure function. So that is called actual property of the system minus property if the gas were at ideal condition. So if I am willing to estimate, this we had actually studied. So this reduced volume is nothing but is equal to B when we are dealing with low to moderate pressures. Okay, so this reduced property concept we are going to use it today, and it is one very important thing when we studied what we studied, that when we are near to critical point we need to consider at least third virial coefficient to predict the correct trend of PV curve, because if we are only considering till second term, so what will happen, there will be some inconsistencies in B value when we are trying to calculate del P del V at constant T and and its second derivative at critical temperature. So that's why we need to go till third term. So this is what we generally, and this additional thing that we learned, Pitzer correlation, Z is nothing but Z naught plus omega into Z prime, and Z naught Z prime charts are available in the literature, and from there this compressibility factor can be estimated. Okay, so this is what we studied in the last class. So this is one way of estimating real behavior of gas. Now we have studied real behavior of gas, and we were stuck at here that ds, this equation cv by t dt, and this cp by dt t dt plus this term. So for ideal as well as real gases, this term is not going to be zero. I'm sorry, I made a mistake earlier. So these two terms for real gas will be different, and that is what we are going to do in today's class. So we have studied this. I just said it that any extensive property, uh, m, let's say it is an extensive property, so its residual function or departure function can be estimated at same temperature and same pressure as its actual value when the gas is behaving real, minus if the gas if were at ideal. So ideal condition is denoted by zeroth sign. Okay, yeah. So yes, so if we put this equation of dH, this we have studied. dH is equal to Cp dt plus V minus T del V del T at constant pressure dP. Okay, so this is what equation is written. So let's say I want to estimate the residue function. So what will be residue function? Residue function is defined as actual property minus ideal property. So what will be my ideal enthalpy change dH? It will be just Cp dt. So my H minus H naught will be this term minus H naught, that is Cp dt. So we get this particular term. Now if we break this term, so it will be VdP. Our limit will be P is equal to 0 to P. Why P is equal to 0? P is equal to 0 denotes ideal gas, and P is actual pressure of the system when the gas is not at ideal state. So my H minus H naught will be equal to integration of 0 to P V minus T del V del P at constant temperature del V del T at constant pressure dP. Yes. So now if I am breaking this term, so it will be VdP minus T into del V del T at constant pressure dP. Now let's say that VdP. So I am writing differential of PVS. What can I write? I can write PdV plus VdP. So what will be differential of VdP? What will be this VdP term? VdP term will be equal to dPV minus PdV. So that is what I am replacing here. So VdP is dPV. So as it is PV, so our limit will be for ideal gas PV is equal to RT. So RT to actual PV value minus this term P into dV. If gas were ideal, so V infinite volume, I am saying it to any volume V. Plus, now this last term. So what can I write? Del V del T at constant pressure into dP. This term can be substituted as minus of del P del T at constant volume dV. So if I am putting this value here, so this minus minus will be plus, and I will be left with this term. So my equation will be like PV minus RT plus this particular integration minus P into whole dV. So for ideal gas, no, for any gas, Z is compressibility factor is defined as Z is equal to PV by RT. So my PV will be equal to ZRT. So RT is common, Z minus 1 plus this equation. So this is the residual enthalpy we can calculate. Okay. Now let's say I want to find residual entropy. So residual entropy, what was the actual entropy? Actual entropy of the system was by this equation, correct? Cp by T dt minus del V del T at constant pressure dP. Cp by T dt minus del V del T at constant pressure dP. Now, what if gas were ideal? So if gas were ideal, we can replace V by T as R by P. Okay. So R by P dP. This will not be zero. This will be V by T. Del V by del T at constant pressure will be R by P into dP as it is. So if I put this, so S minus S naught. So this term, actual S minus S naught. So this Cp dt will be cancelling out, and we will be only left with this particular term. Now again, we do the same thing. What will be my minus del V del T at constant pressure equal to del P del T at constant volume dV plus R by P dP. Okay. So now also again this term remains as it is. Now how can I replace R by P dP? So d of PV, differential of PV is defined as P dV plus VdP, correct? So what is dPV by, if I divide this equation both side by PV, so my dPV by PV is equal to dV by V plus dP by P. So I can replace my dP by P as dPV by PV minus dV by V. That is what I have done. Okay, and then we put some values. So I just combine these two terms, and this term as it is, PV by RT is nothing but Z. So residual entropy will be R into ln Z plus V infinite to V del P del T at constant volume minus R by V dV. So let's say I am now dealing with some van der Waals equation of state. So this del P by del T at constant volume is not going to P by T for ideal gas, for real gas. Correct. Similarly, here also, if my gas were ideal, then my residual function will be 0, because residual, what is residual function saying? How it is deviating from ideality. So if gas is ideal only, so their residual function will be 0. We can even verify it if I keep P by T here. So this term will be 0, and for ideal gas, Z is equal to 1. So this whole term will be 0. That means that my gas is behaving ideally. Similarly, here also you can obtain that this P by T will be R by V. Yes, P by T will be equal to R T. Yes, R by V. So this term goes to 0. And for ideal gas, Z is equal to 1. So this whole term goes to 0 for any. So remember, when I am asking, or anyone is asking, that what is the residual property value for ideal gas, so that is nothing but 0 for enthalpy, entropy. Okay. So now let's move ahead. Let's say I am having this HR and residual enthalpy and residual entropy equations, and now I want to deal with how can I how can I predict this HR and SR values for various equation of states. So let's say I am first dealing with van der Waals equation of states. So equation is P plus A by V square, V minus B is equal to RT. So my P will be equal to RT divided by V minus B minus A by V square. So my del P by del T at constant volume, del P by del T at constant volume is constant. So this differential will be R divided by V minus B, and this term is going to be 0, because there is nothing to differentiate with respect to T. So my what will be my residual enthalpy? RT into Z minus 1 plus integration of this equation, V infinite to V T into del P del T. So T into this term R divided by V minus P, V minus B minus P into dV. So if I substitute this, it comes out that this term RT divided by V minus B minus P is nothing but A divided by V square. And if I am integrating this, I get that residual enthalpy will be PV minus RT minus A by V for in case of when we are dealing with van der Waals equation of state. Okay. Similarly, what will be residual enthalpy, residual entropy for van der Waals equation of state? So it will be R into ln Z. That term will be as it is, and del P del T will be R divided by V minus B. So that's what R divided by V minus B minus R by V dV. So the same term the same term I substituted, and then it's just integration ln V minus B minus ln V. So if I combine all these terms, so R into this will be, these are all in logarithmic terms, so plus will be multiplied and minus will be divided. So Z into V minus B by V. So Z is nothing but PV by RT. So VV cancels out. So we remain with this, S residual is SR into ln of PV minus B by RT. Okay. So this is how we can derive this for residual enthalpy and residual entropy in case of van der Waals equation of state. Okay. So let's have a look at something important. So this was just very easy van der Waals equation of state. When we deal with some other equation of state where the equations are already complex, so let's say these equations, it will be here. This sorry, where did it go? Yeah, this kind of equation of state with we are having value of epsilon and sigma 4. Let's say we are dealing with Pang-Robinson equation of state. So my sigma and epsilon will be 1 plus square root of 2, 1 minus square root of 2. Omega is 0.07780 and psi is 0.45724. And alpha value is nothing but this very complex equation. Okay, so this is my Pang-Robinson equation of state. And when I try to find out this in case of when we are dealing with Pang-Robinson equation of state, so we get that this HR by RT is coming out to be something like this: 1.5 A divided by RB T raised to 1.5 ln V divided by V plus B plus Z minus 1. And similarly, if I found calculate residual entropy, so it will be ln V minus B by RT minus 0.5 A divided by BR T raised to 1.5 and into multiplied with this ln term. Okay, so if we see that this derivation itself is very tedious to find out for each equation of state. So when we are dealing with equation of state approach to find the residual enthalpy and residual entropy, so can there be any other way we can use it? So in last class, I discussed that in starting of this class only, we discussed that we can also use this compressibility factor method. Okay, so V is nothing but Z unto RT by P. Okay, so what was my original equation of residual enthalpy? This was the equation that integration 0 to P V minus T del V del T at constant pressure into dP. Okay, so let's say I'm saying that V is equal to Z into RT by P. So what will be my del V by del T at constant pressure? So it will be del by del T at of Z into R into T by P. If I break this down, so let's say T constant, let's say ZR by P constant, R is constant, P is constant, only Z will depend on temperature. So let's say Z into R by P is constant, differentiation of T is 1 plus TR by P is constant, differentiation of Z is del Z by del T at constant pressure. Okay, so what will be my residual volume if I replace this term here? So V is nothing but Z into RT by P minus these terms T into del V del T at constant pressure. So minus T into this Z RT by P minus T was 1, T was already there. So T square into R by P into del Z del T at constant pressure dP. So these two terms cancel out and we are left with minus RT square integration 0 to P del Z by del T at constant pressure into dP by P. Correct. Now let's say I am not writing in terms of T and P, but I want to write it in terms of TR and PR. So what can I write? TR is equal to T divided by TC. So what will be my T? T will be equal to TRTC. So here I substitute TS TRTC. So TR square TC square. Correct. Then del Z del T. So T again I can replace here TS DRTC, PS PRPC, and here also PS PRPC. Okay. So my equation will be what will it be? My this term. So TC is something constant, so it can't vary. So TC can comes out from here and one TC will be cancelling out. So my HR by RTC will be equal to minus TR square into integration 0 to PR del Z by del TR at constant PR. Here also PC is constant, so PC can come out, PC cancels out, so it is nothing but dPR by PR. So this is what residual enthalpy is in case when we are writing it in terms of compressibility factor with reduced temperature and reduced pressures. Okay. Similarly, I can also find residual entropy that is defined as SR is equal to integration 0 to P minus del V del T at constant pressure plus R by P dP. So this term we found out what was del V del T at constant pressure. It is ZR by P plus TR by P del Z del T at constant pressure. So this is the first term minus of this. So both are having minus and plus R by P dP. Now from whole this R by P we can keep common. So it is minus Z, this plus 1 and this term minus T. Okay, it is here del Z. It has, I was trying to rub something and it went out. So del Z by del T at constant pressure dP. So same thing we can again do it here, that P I can keep inside because P is equation is P dependent. So I need to integrate. So I should not have taken it out. So this equation remains as it is. T is at TRTC, P is PRPC, PRPC. Okay. So PC again here cancels out. So this equation is nothing but if I keep minus out of this whole thing, so it will be Z minus 1 plus TR del Z by. Why here TR? Because TC is constant, so TC will be out from here. So T by TC is TR. So plus TR del Z by del TR at constant PR dPR by PR. So this is what I get for residual entropy SR by R, and similarly HR by RTC. Okay. So these obeys the three parameter law of corresponding states. So Z I can write as Z naught plus omega into Z prime. So similarly I can write down this for whole all equations, that H residual will be equal to H naught plus omega into H prime. So H naught is this term, this same term that we derived, with Z as Z naught ideal gas plus omega into H prime, same equation with Z prime. So if we, so I can also write this as HR residual enthalpy. I can write it as HR by RTC plus omega into HR by RTC prime. Okay. So this term comes out. Okay, so this is how I can estimate residual enthalpies. And for this charts are proposed. So if we look at some charts, so charts will be at the end. Charts are available. Let's try to go into appendix first. Okay, so here if we see, these are the tables. So see, this is Z naught and Z prime tables. Then similarly, see H naught by RTC, HR naught by RTC, and HR prime by RTC. So if we know these two terms, we can easily estimate the value of residual enthalpy of gas. So these are called Lee-Kesler chart. Similarly, the same equation I can write it down in terms of entropy also. So entropy SR is nothing but S naught plus omega into S prime. So if I write down this equation for 0 and 1 term, or 0 and prime, not and prime term. So similar thing I will get SR by R naught plus omega into SR by R prime. Okay. So if we see here, you see SR by R naught term and SR by R prime term for various PR and TR. If we know this, then we can easily estimate the uh, values of this residual properties SR by R and SR by R naught and prime term. So these charts are proposed, and these charts are generally called Lee-Kesler chart. So if you know the data of PR and TR, then it is easy to estimate these residual properties. Now, if I look at Virial, the third way. So what we studied last class to find the PVT behavior of gas, that was Virial equation of state. So if I use Virial equation of state, so for Virial equation of state, Z is defined as 1 plus BP by RT, or pressure explicit, it is similar. Yeah. So if I replace P as PRPC and T as TRTC, so I get that Z is 1 plus BPC by RTC, PR by TR. Now I can write down again Z as PV by RT, and this is for low to moderate pressure because we are only considering our term still B value. Okay. So yeah. So Z is PV by RT. If I replace PV by RT, so my V will be equal to RT by P into 1 plus BP by RT. That is nothing but RT by P plus B. So what was my original equation of enthalpy? This H residual was this 0 to P, V minus T del V del T at constant pressure dP. So if I find del V del T at constant pressure, so this will be equal to del V del T. So R by P, R is constant, P is constant, because so we are only left with T. So differentiation of T with respect to T is 1. So this term is R by P, and B depends on T. We had a look in last class. So I can write down this as del B by del T at constant pressure. Okay, so if I replace these terms in this equation, so V was my RT by P plus B, minus T into this term. So minus T del B del T at constant pressure minus T into R by P. So these two terms cancels out and we are only left with 0 to P B minus T del B del T at constant pressure dP. So if I integrate from 0 to P, so I am just left with B minus T dB by dt into P. So this is how I can calculate residual enthalpy in case of using virial equation of state, and when we are going till we are dealing with low to moderate pressures where we can truncate till we can have expressions till B. Okay, so if we do the similar exercise, this virial equation of state exercise for residual entropy calculations, correct? So this is my residual entropy. SR is equal to minus 0 to P minus del V del T at constant pressure plus R by P into dP. Okay, so what is this del V del T at constant pressure? We found out del V del T at constant pressure plus R by P minus, okay, this minus I have taken out. So this will be minus, okay. So minus R by P dP. So this terms cancels out, and if I differentiate it, so P minus 0 will be the limit. So P into dB dt at dB dt. So this will be my residual entropy. So this is how we can estimate residual enthalpy and residual entropy. So we here learned that we can estimate residual enthalpy, residual entropy using first equation of state. Those are Peng-Robinson. We had a look at Van der Waals equation of state, how to do this, how to perform these calculations in case of Van der Waals equation of state. Then from there we moved to Peng-Robinson. We have not derived how to, what is the value for Peng-Robinson equation of state. Then we took the second approach, compressibility factor approach, and we tried to include residual temperature, residual pressure in that, and we found out the values of TRN, HR and SR. Then the third way was virial equation of state, where we used for low to moderate pressure, where we can neglect where we can neglect terms higher than B. So if we truncate it till B, so we get what are the residual enthalpy and entropy uh, in case of virial equation of state. So these terms are very important, and for this Z, using this Z compressibility factor approach, we need to know this. We need to have Lee-Kesler charts, and we had a look at this Lee-Kesler charts. So if you know the value of this, you need to calculate this term HR naught by RTC and HR1 by RTC for various value. These charts are available for various values of PR. Let's say it is going from 0.01 to 1 and TR is going from 0.3 to 4, and further PR is going from 1 to 10 and TR is going from zero point 0.3 to 1 point, sorry, what was the value? Yes, 0.3 to total 4. So this is how we can use the Lee-Kesler chart. So this was all about how to estimate residual properties, residual enthalpies and residual entropies. Okay. Okay, so now so this whole discussion was in case of closed system. We derived all these. Okay, let's once again go through this. So these whole equations were for closed system. When we are dealing with closed system, we first derived this first second law of combined equation, and this was just for closed system. What does closed system mean? Closed system is saying that energy can transfer but mass cannot transfer. So number of molecules remain constant in the closed system. Okay, but now let's say we are dealing with open system. So what does this mean when I am saying open system? Open system meaning energy will definitely exchange, but mass will also exchange with the surrounding. System will also exchange the mass with its surrounding. Okay, so let's say I'm now trying to deal with open system. So for closed system, we had looked at this particular equations. Sorry. Uh, yes, we had looked at this equation that U is function of entropy and volume, and I can write it down as du is equal to TdS minus PdV. Now H is S comma P function of entropy and pressure, and I can write it down dH as TdS plus VdP. Then A is nothing but Helmholtz free energy, that is function of temperature and volume, and I can estimate dA as minus SdT minus PdV, and Gibbs free energy as a function of temperature and pressure, so I can estimate dG as VdP minus SdT. Okay, so now when I am dealing with open system, so I said that we also need to take U will be function of number of moles of particular component. Let's say I'm currently dealing with single component system. So my U will be function of S comma V comma N. So I can write down du as del u, if let's say from here, what can I write? Du is equal to del u del s at constant v comma n ds plus del u del v constant s comma n dv plus del u del n constant s comma v dn. Okay. Similarly, I can write it down enthalpy S. Enthalpy is a function of S comma P comma N. So I can write it down dH as del H by del S into ds at constant Pn plus del H by del P at constant Sn into dP plus del H by del N into dN at constant entropy and pressures. Okay. Similarly, Helmholtz free energy is a function of T, V and additional N. So dA I can write it down as del A by del T at constant Vn into dt. Similarly, plus del A by del V at constant Tn dV plus del A by del N constant Tv dN. Similarly, the most practical application dg as TPN can be written down as dg as del G by del T dt with constant Pn plus del G by del P dP at constant Tn plus del G by del N dN at constant T comma P. Okay. So now let's say I am saying that del U by del N as U. Okay. Let's say I am saying that this is my partial uh, molar entropy. Let's say del U del N at constant SV is my U. But what I can write it down, U can be written down as U into N. N is mole. So U molar enthalpy into mole. So it will be my total. Total property. So if I replace U as UN here, so it will be U constant del n by del n will be 1 plus n constant del u del n at constant SV. So this is not true. This is contradicting, right? Contradictory. So what does this suggest? That U and U we can't keep constant as n is varying. So if n is going to vary, then my u will be going to vary. So both we cannot keep constant. So that's why we move to Gibbs free energy, that is defined as G Gibbs free energy total, that is nothing but n into molar Gibbs free energy and into G. So del G del N will be equal to del by del N of Ng. So it will be equal to G plus this particular term. Okay. My dg is nothing but vdp minus sdt. So we have derived that del g by del n at constant Tp is equal to small g. This we have defined and we have derived that for constant temperature pressure conditions only. This is equal to partial molar. Sorry, not partial molar. I'm really sorry for this word. It is equal to just molar Gibbs free energy. So this term has to be equal to 0. Okay. So let's say I'm now dealing with U is equal to N into U. This we have already written. So let's say I'm calculating differential. So my du will be is equal to N into small du plus U into small dn. Okay. So n into what is du? Du is nothing but TdS minus PdV. Okay, so I'm writing it as TdS minus PdV plus UdN. I'm keeping it as it is. Okay, now let's say what is this term? T into DNS. Let's say I want to write T into DNS. This term is N into T into ds. So let's say I want to write T into d of ns. So it will be equal to n into ds plus S into dn. So I am additionally writing S into dn by adding this. So I need to subtract S into dn and it is multiplied with T. So minus Ts into dn I subtracted. Similarly, I want to write it down this term as V into N, differential of V into N. So I need to, as it is in minus, so I need to add additional term PV into dn. Correct? So these two terms are additional and UDN remains as it is. So my equation will be equal to this N into S will be equal to S, V into N will be equal to capital V, and this DN plus dn is constant in this whole thing, so it is u minus ts plus pv. So what is my u minus ts plus pv? U plus pv is h minus ts is nothing but g. So I can write it down as du is equal to tds minus pdv plus g into dn for open system. Similarly, if I derive this for enthalpy, Helmholtz free energy and Gibbs free energy, we get this initial equation for closed system was TdS plus VdP, and we only need to add GdN term. Similarly, for dA minus PdV minus SdT was there, we only need to add GdN, and similarly for dG, VdP minus SdT plus we need to add GdN in case of open system. So how can I define this molar Gibbs free energy? So G I can write it down as del U del N at constant SV, that is equal to del H del N at constant SP, that is equal to del A del N at constant VT, that is equal to del G del N at constant TP. This gives us the value of G. So you see that for this is only true del U del N at constant SV is nothing, it's not small u, but it is small g. Okay. So G is called partial molar not partial. I'm sorry, I'm repeating these words. It's not partial. Partial property we will look in upcoming classes. This is just molar Gibbs free energy, or it is also known as chemical potential of a substance. Okay. So chemical potential of substance, what is it? It is molar specific property at isothermal isobaric potential. Molar specific isothermal isobaric potential. Okay, so that is nothing but chemical potential. So if it is asked you what is chemical potential, so you should say that molar Gibbs free energy at constant temperature pressure, or molar internal energy at constant entropy volume, or molar enthalpy at constant entropy pressure, or molar Helmholtz free energy at constant volume temperature. Okay. So G, look, okay, let's try to derive very important phenomena of chemical engineering thermodynamics. So this equation I can write it down as du is equal to TdS minus PdV plus mu dn. Okay. So let's say I'm doing the same thing once again here. So let's say I'm keeping du as it is and dt into ds is there. So let's say I want to write differential of ts. So I need to subtract minus s dt. Similarly, let's say I want to write down here differential of PV. So it is already negative. So I need to add differential of VDP, and similarly mu dn is there. So I want to write differential of mu n. So I need to subtract n into d mu term. So if I take u d of u minus ts plus PV, that will be equal to minus s dt plus VDP minus n into d mu plus this additional term d of mu into n. Okay. Now, what is u minus ts plus pv? So u minus ts, u plus pv is h minus ts is nothing but g, Gibbs free energy. So this term is nothing but dg. This remains as it is, minus s dt plus vdp minus n into d mu, and this term mu into n. What is mu into n? Del g del n at constant tp is g. So nothing but mu. So mu into n will be equal to my total Gibbs free energy G. So these two terms cancels out and we are only left with SDP minus VDP plus N into d mu is equal to 0. And this is called Gibbs-Duhem equation, and this is really very important phenomena. What does this say? This is saying very important thing. This is saying that when I am dealing with a single component open system, so we cannot vary T, P and mu at the same time. What does this mean? Let's say I'm fixing my temperature and pressure. So mu is automatically fixed. So when I'm dealing with this kind of variables, I cannot keep T, P and mu constant. Okay, so any system cannot have TP and mu constant, because if T and P is fixed, mu is automatically fixed. If P and mu is fixed, T is automatically fixed, or if mu and T is fixed, P is automatically fixed. So this is called Gibbs-Duhem equation, and this is really very important finding. Okay, so this whole thing was for single component system. Let's say I was dealing with only one component. But reality, single component system definitely exist, but multi-component systems are more practical than single component systems. I can write down, let's say, same thing. U is a function of s comma v comma n. So I can write it down du as same. Now let's say n component system. So let's say n1, n2, n3 like that. So what can I write? Du is equal to del u del s into v constant and all n's constant, n1, n2 to n, all n constants into ds, plus similarly del u into del v entropy constant and all other n1, n2 to till n constants into dv, plus again del u del n1. Let's say I'm now I have n1, n2, n3 like that. So let's say I'm first differentiating this with n1. So del u del n1 at constant sv. N1 is only varying, n2, n3 other remains constant into dn1, plus del u by del n2 sv n1, n2 all constants into dn2. Now what did we look at in this single component system? That del u del n a constant entropy and volume is nothing but Gibbs free energy. Sorry, not parcel, molar Gibbs free energy, or it is chemical potential. Okay. So this is how I can write it down. Instead of del u del n1, I can write it down as mu1 dn1 plus mu2 dn2 plus mu3 dn3, similar up to whatever number of components you have in your system. Similarly, let's say I want to write it down for enthalpy. So enthalpy is function of s comma p comma n. So I can write it down ds is equal to del h by del s into ds, but this term as constant p and all n's, n1, n2, n3 all are kept constant. Plus now with respect to p, so del h by del p constant s and all n's, n1, n2 so on into dp, plus del h by del n1 into dn1 constant s p n2 n3 and so, plus similarly del h by del n2 into dn2 constant s p n1 n3 so on. Okay, now I can also write it down similar. So this term will be equal to mu1 del h by del n1 at constant sp is nothing but mu, chemical potential. So I can replace this with mu1 dn1 plus mu2 dn2. Similarly, if I write it down for Helmholtz free energy, so I can write it down as dI is equal to del A by del T, constant V, N1, N2, so on, dt, plus del A by del V, constant T, N1, N2, so on, dV, plus del A by del N1, dN1, keeping N1 N2, N3 and other till N constants, plus del A by del N2. Only n2 is varying, n1, n3 all other are constant. So this term is also mu1 and mu2. Okay. Similarly, I can write this down for Gibbs free energy. So dg is del g del t constant pressure and all other n's, dt, plus del g del p constant temperature all other n's into dp, plus del g now del n1 tp n2 n3 all other n's constant except n1 dn1, plus del g del n2 tp n1 n3 dn2. Okay, so what can I simplify it? This was du is equal to, this is t tds minus pdv plus mu1 dn1 plus mu2 dn2 plus mu3 dn3 so on. So I can write it down as du is equal to tds minus pdv plus summation I is equal to 1 to n mu I dni. What does this mean? I is equal to 1 to n. So it is mu1 dn1 plus mu2 dn2 plus mu3 dn3, so on. So this term, similarly, I want to write it down for enthalpy. So my dH is equal to TdS plus VdP plus summation I is equal to 1 to n mu I dni. Similarly, for dA, minus SDT minus VdP plus summation I is equal to 1 to n mu I dni. And similarly, dg is vdp minus sdt plus summation I is equal to 1 to n mu I dni. So first, what did we see? First, we write it down for closed system, just function of entropy, pressure, temperature, volume, temperature, pressure. So equations were very simple. Only TdS minus PdV, TdS plus VdP minus SDT minus PdV, VdP minus SDT. When I went from closed system to single component open system, so what did I had to do? I had to add this mu dn term in all equations. When I am dealing from I am going from single component open system to multi-component open system. So what do I need to do now? Mu1 dn1 plus mu2 dn2 plus mu3 dn3, so on. So I need to add this additional term, summation of I is equal to 1 to n mu I dni. Okay. So how can I define now mu? So my mu is nothing but del u del ni. Mu I, let's say mu1, mu2, mu3, like that. So mu I will be equal to del u del ni at s constant, v constant, and n, all n constant other than I. So n I is not equal to j. Similarly, del h del ni at constant entropy, pressure, and n all n's where I is not equal to j. Similarly, del A, del Ni at constant temperature, volume, and Ni not equal to J, and dg, del G, del Ni at constant temperature, pressure, and not I not equal to J. So this is how I can define my chemical potential. Now, what will be my Gibbs-Duhem equation? So it will be what was earlier. It was the SDT minus VdP plus mu dn n into d mu. So now it will be equal to SDT minus VdP plus summation I is equal to 1 to n and I d mu I equal to 0. Okay, so this will be my now this will be my Gibbs-Duhem equation. Let's say I am dealing with constant temperature and pressure. So this term cancels out, this term cancels out. So we are only dealing with summation of I is equal to 1 to n, ni d mu I is equal to 0. So let's say I am dividing both sides by total number of components n. So this ni by n will be xi. So I is equal to 1 to n, xi into d mu I is equal to 0. So this is what Gibbs-Duhem equation in open system, multi-component open system says. Summation I is equal to 1 to n xi d mu I is equal to 0. Okay. Now, now we need to ask these questions, that internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy, those were called thermodynamic potentials. Why were they called thermodynamic potential? What are the properties for thermodynamic potentials? So the value of that particular potential is independent of integration path. So that is true for U, H, A, and G. So that's why those are state function. They don't depend on path. Then second property is those are measured in terms of energy. So G, Gibbs free energy, we are anyway calling it energy. Gibbs free energy, Helmholtz free energy, they have units of energy. Okay. Now the third term is minima, denotes the stable equilibrium. So when we were dealing with that closed system, du at constant SV should be equal to 0, dH at SP equal to 0, dA at TV is equal to 0, and dG at TP is equal to 0. Now let's talk about chemical potential. So is chemical potential independent of integration path? Yes, chemical potential is independent of integration path. It does not depend on path because mu is the system property. Okay, so that's why mu is independent of integration path. So that fulfills the criteria for chemical criteria for thermodynamic potential. Now, second term is measured in units of energy. So if mu is measured in terms of energy, yes, mu is measured in terms of energy. We define mu as del J del Ni at constant Tp, Ni is equal to not equal to J. So this is the energy unit. Okay. Now third term is minima denotes the stable equilibrium. That is not true because we don't have this condition that d mu at Tp is equal to 0. But we have that xi d mu I should be equal to 0. So what is mu? Mu is combined characteristic of energy and force. So it has unique place of own. So mu is not really a true thermodynamic potential, but we call it a chemical potential, which is driving any chemical process that is happening. Okay, so this is what we learned. Now let's have a look at some very small derivations. So this del u del n at constant s comma v. So what is my small u? Small u is nothing but capital U by n dn. So this term will be equal to minus u by n square. That is nothing but minus of u by n. Similarly, del v by del n. What will be my del v by del n? Similarly, v by n. So minus v by n square minus small v molar by n. Okay, what is my del s? Del s by del n at u comma v. So that is nothing but minus u into tn, u by tn plus p into v by tn. Correct? Du is nothing but TdS minus PdV in that way. Okay, so let's say I'm writing now for capital S total property. So del S by del N at U comma V is equal to del by del N at what can I write? S as N into S. So if I break this down, so N remains constant, del S by del N plus S remains constant, del N by del N is 1. And if I put del S by del N from here minus U n constant minus u by tn plus pv by tn plus s. So I get that minus u by t minus u n cancels out by t plus p into v by t plus small s. Okay. So this is nothing but u. If I keep minus constant, then u minus ts plus pv divided by t. So what is this? U minus ts plus pv. U plus pv is h minus ts is nothing but mu. So this is how you can also derive this thing in other way. So del S by del N at constant u comma v is nothing but minus of mu by t. Okay. So this is a very simple thing, combined first and second law of thermodynamics for a single component system. These all equations we looked at are only applicable when we are only dealing with PV kind of work. We are not having any kind of other work present in our system. Okay. So this is all what we had looked at today's lecture. Let's quickly revise it and then we go through some equations. So in last class, we learned that we really need to know the PVT behavior of gases, because for ideal gas, dH, du were equal to just CPdT or CUdT, and these terms cancelled out. So what if these terms are not cancelled out, or these terms are not zero? This term is not zero. So that's why we moved from ideal gas to real gas. We looked at Van der Waals equation of state, SR equation of state, SRK equation of state, RK equation of state, and Planck-Robinson equation of state. Okay, so this first way, we derived these values of residual enthalpy and residual entropy, and we tried to substitute this equation, this del P del T at constant volume term for various equation of state. Let's say for Van der Waals equation of state, we found this out, and for with in case of residual enthalpy and entropy, and then we had a look at Planck-Robinson equation of state. Then in last class, we had looked at PVT behavior of gas using compressibility factor. So we are just using V is equal to zeta RT by P, and we are we are breaking our equation, and we are finding H residual and S residual. And from Lee-Kesler chart that I had shown, you have values of this HR by RTC naught and HR by RTC prime. So if you know that, you can calculate the value of H residual. Similarly, for S residual also, S residual by R. If you know this two term, you can calculate S residual from Lee-Kesler charts. And the third way, in last class, we had looked at virial equation of state. So for low to moderate pressures, these only till terms till B are significant. So my V is equal to this, and from here we estimate del V del T at constant pressure, and we find out residual enthalpy and entropy. Now our all discussion till here was for closed system. So for now moving from closed to open system, we need to also look at number of molecules or moles. So that is what we incorporated here, and we find out that del G del N at constant Tp is only is equal to G, but del U del N at constant Tp del U del N at constant SV is not equal to small u. This is what we find out. And for single component open system, we only need to add this mu dn term, and we can find out mu by this way: del u del n at constant sv equal to del h del n at constant sp is equal to del a del n at constant vt, and del g del n at constant tp is nothing but molar Gibbs-Duhem energy, or which is called chemical potential. From there we derived Gibbs-Duhem equation, very important equation, that says that S dt minus V dp plus mu dn is equal to 0. So we cannot vary Tp and mu all three at the same time. If we are fixing T and P, mu is automatically fixed. This is really very important, very important thing. Then we move from single component open system to multi-component open system, and we only had to add from derivation, we only had to add summation I is equal to 1 to n mu I dni term in all du, dh, dA and dg term. And again Gibbs-Duhem equation, then we can write it as I is equal to 1 to n ni d mu I instead of just n into d mu. Okay. And for constant temperature pressure, this will be equal to 0, and this is our remaining equation. Okay. Now we had a question that if chemical potential is truly a thermodynamic potential. So no, it is not truly a thermodynamic potential, because value is independent of integration path, and chemical potential is also measured in units of energy, but its minima does not denote any stable equilibrium. So chemical potential is not truly a thermodynamic potential, but it has its unique place of own. And then we derived in other way that how del s del n at u comma v is minus mu by t. Okay. So this is all we had look, and this very important to remember that this whole discussion is only for PV kind of work. For any other kind of work, we need to add more terms with additions. Okay. So this is all what we had look at. So now let's quickly go through some simple question answers. So let's say a gas Tc is equal to 283.1 Kelvin and Pc is equal to 51.17 bar. This gas is obeying the equation of state given by P into V minus B is equal to RT. So we need to find the value of B. So what is this? This is nothing but modified. This is nothing but Van der Waals equation of state with a term is not present in the system. So how did we derive value of B for Van der Waals equation of state? Let's quickly go through that derivation. So we had written this equation P plus A by V square, P minus B is equal to RT. So my in terms of critical point, PC is equal to RTC divided by VC minus B minus A by VC square. And we know that at critical point del PC by del VC at constant TC is equal to 0, and del square PC by del VC square at constant TC is equal to 0. So my del PC by del VC at constant TC was nothing but I need to differentiate with respect to VC. So it was nothing but 1 upon V term. So it is minus 1 upon V square. So minus RTC divided by VC minus B whole square. And 1 upon V square is minus 2 upon V cube. So plus 2 into A by V cube is equal to 0. So I get this first equation. Then similarly, if I derive this equation again, derivative, find a derivative with respect to V once again. So I get this equation 2RTC divided by VC minus B whole cube minus 6A divided by VC raised to 4. So this is equal to, this is also 0 at critical point. So we can equate these two. Now if I divide 1 by 2, so I get that VC is equal to 3B. And if I put VC is equal to 3B in, or B is equal to VC by 3 in this equation, original van der Waals equation of this. So we find out that so we find out that A is nothing but 9 by 8 RTC VC. Now in practical, VC is, in terms of VC, it is difficult to measure. So if we can have A and B in terms of PC and TC, so that is what we try to find out. RTC by VC minus B was VC by 3 minus A by VC square. So I put A value and I get that VC is 3 RTC by 8 PC. And if I put these values again to our original equation, so I find out that A is 27, A is nothing but 27 by 64 R square TC square by PC, and B is nothing but RTC by 8 PC. Okay, so now what is told to us that intermolecular interactions can be neglected. So we are only left with this B term. So what is my B? B is nothing but RTC by 8 PC. Okay, so what will I do here? I will find out my B as R into TC by PC. So my R is 8.314. TC is nothing but 283.1 and PC is nothing but 51.17 into 10 raised to 5. Okay, so if I find this out, I find that A is this, sorry, TC is this, PC is this, R is this, and if I find out B as RTC by 8 PC, so I get that B is equal to 5.75 into 10 raised to minus 5 meter cube per mole. So this is how I can estimate the value of B. Okay, so you can be given any kind of equation of state and you are supposed to find the values of, let's say, just normal equation is also given. P plus A by V square, V minus B is equal to RT, and you are supposed to find the value of intermolecular interaction. So it will be denoted by, A will be denoted by this 27 by 64 R square TC square by PC. Okay. So if that were the equation, we can find out what will be our R value. So let's try to calculate it. It is opening. Okay. So, okay, let's wait for this first. Let's try to do this. This is not required. Let's say my A, my TC is equal to, what is my TC? Okay, let me not write down here. Open one TypeScript. Okay. So my TC is equal to, what is my TC given as 40, sorry, not this question. Yeah, 283.1 Kelvin, 283.1. In my PC is equal to 51.17. I am writing in SI units into 10 raised to 5 in SI units. And my R will be equal to 8.314 in SI units. So what is my B? B is nothing but R into TC divided by 8 into PC. So if I run this, I will be able to see what is my value of B, 5.7497 into 10 raised to minus 5. That is what we are getting. So let's say I'm finding A. So A is nothing but 27 by 64 into R square into TC square divided by PC. So what will be my A? Is 0.4567. Okay, so this is how you can also calculate the value of A in SI units if you are asked to find. Okay, so you just need to remember these two formulas in case of Van der Waals equation of state, that E is 27 by 64 R square TC square by PC and B is RTC by 8 PC. Okay, so now let's move ahead to next question. The critical constants of ammonia are Tc is equal to 405.5 Kelvin and Pc is equal to 112.77 bar. So what is eccentric factor? And we are given that saturation pressure of ammonia at 283.85 Kelvin is 6.150 bar. So what is eccentric factor? Let's quickly go through this. It's a mistake here. It should be -1 in this plot. It should be -1 here. Okay. So what is my eccentric factor? So when I plot log 10 PR set versus 1 upon TR, so I get a straight line for simple fluids at TR is equal to zero point 0.7. This value is -1. Log 10 PR set value is -1. Okay. And for other gases like water vapor or ethanol, so it is not 1. If it were really following two parameter law of corresponding states, then for all fluids, this one line we would have observed, but that is not the true case. So this omega eccentric factor is added. So how omega is calculated? Omega is nothing but -1 minus log 10 PR set at TR is equal to zero point 0.7. So let's try to first find out what is the value of TR. Okay. So what is given to me in question? That um, this, yeah, TC is equal to 405.5 Kelvin. TC is equal to 405.5 Kelvin. Then PC is equal to 112.77 bar into 10 raised to 5 pascals. That is my PC value. And this data is given to us that PSAT is equal to, what is my PSAT? 6.150 into 10 raised to 5. I am writing in SI units, 10 raised to 5 pascals. And T is equal to, Tsat is equal to corresponding that temperature, or just T is equal to, what am I getting? 283.85 kelvins. Okay. So for eccentric factor, what do I need to first know? I need to first know this term. Sorry, for eccentric factor, first I need to know what is my TR. I should be at TR is equal to 0.7. So let's first try to find out TR. TR is equal to my Tsat divided by TC. So let's see what are we getting for TR. So my TR is exactly 0.7. So whatever my this term PR set, it is at TR is equal to 0.7, will be at 0.7. So what is my PR set? So PR set is equal to P set divided by PC. Okay. So this is what I am finding at my PR set. So what I need to do now, my omega is -1 minus log 10 this PR set. So my omega is equal to -1 minus log 10. I need to write log 10. Sorry, log 10. Yeah, this log 10 of this PR set. Okay, so if I calculate it, it is 0.2633. For whichever gas it is, we are getting our eccentric factor as 0.282633. So this is surely not one ideal gas. Okay, so 0.2633 we are getting. So you can have a look at this solution. TC, PC, PSAT, TSAT we have. The main problem is when you are not having this TR is equal to 0.7, then you need to find what will be my PR set at TR is equal to 0.7. So if here it was by default TR was 0.7, so that PSAT was already at TR is equal to 0.7. But if you are not given at TR is equal to 0.7, then this is the this will be one issue. So this is how we can so this is how we can estimate the value of eccentric factors. Okay, so if you have a look at this appendix B, yes, here. So see, omega values are like this 0.012, 0.1, 0.152, like that. Okay, so these are when when you are given the value of, when you are supposed to find the value of omega from some tables for your, let's say, project or some kind of questions that you are not given omega, so you need to find the value of omega from this particular table, that is from book Introduction to Chemical Engineering Thermodynamics by Smith. Okay, so let's move ahead. So the compressibility factor Z for a three parameter law can be expressed as, how can I express Z as for any three parameter law? So how can I do it? So this we had looked in the last class. This we had looked at last class, that I'm writing my for low to moderate pressure, I'm writing that PV by RT is 1 plus BP by RT. This P is PC into PR and T is nothing but TC into TR. So this BPC by RTC is nothing but B naught plus omega into B prime for all non-polar molecules. So if I replace B naught plus omega into B prime here, so I will be with 1 plus B naught into PR by TR plus omega into B prime PR by TR. So this term 1 plus B naught PR by TR is called Z naught, and omega into omega is as it is, and B prime PR by TR is called, this is called Z0 and this is called Z prime. So this is three parameter, as per question. For three parameter law, Z can be expressed as Z is equal to Z0 plus omega into Z1. Correct? So if you know how to find Z0 and Z prime, in last class we had taken one sample problem for how to find Z0. Let's say I want to find the compressibility factor. So how can I find it? So I can find this using values of Z0 and Z prime. So see, these are my, if you know PR and TR at any, if you know PR and TR for your system, let's say my PR is, let's say my PR is 2 and TR is 1. So for 2 comma 1, my Z0 will be equal to 0.3229 and Z prime will be equal to minus 0.0824. So from this directly, for particular gas, you know the value of omega from these tables that I had shown to you. So from that you can directly estimate the value of Z. So this is the benefit of using three parameter law, in which Z is expressed as Z0 plus omega into Z prime. Okay. We have to choose the wrong statement among the given to us. So the first statement says that chemical potential is an intensive property. What is an intensive property? Intensive property is a property which does not depend on mass of the system or matter of the system. So chemical potential is an intensive property because it will not depend on mass of the system. So this one is a correct system. That is one. Yeah, that is correct statement. Now second, chemical potential has units of energy. Correct? It was del G by del Ni. So it has units of energy. Let's say Gibbs free energy. Okay. Now third system, third option, for a single component system, temperature, pressure and chemical potentials can be varied independently at the same time. This is completely wrong because just now we had looked at and we had derived the Gibbs-Duhem equation that says that S dt minus V dP plus mu n into d mu is equal to 0. So this says that if I am fixing T and P, mu is automatically fixed. So I cannot vary T, P and mu all three at one same time. So we cannot have something T, P and mu varying at the same time. And for multi-component open system, I can write this down as S dt minus VDP plus summation I is equal to 1 to n and I into d mu I is equal to 0. So this statement is completely wrong. which says that for a single component system, temperature, pressure, and chemical potential can be varied independently at the same time. But the correct statement will be cannot be varied and independently at the same time. Okay. Okay, the last statement is under chemical equilibrium. The sum of total chemical potential for each component in different phase is equal to zero. This is also correct. Mu in one phase should be equal to mu in other phase. Okay. So from this we say that this statement C is completely wrong, and it is this statement is something opposite to what we derived from Gibbs-Duhem equation. Okay. Now let's move to next question. Gibbs-Duhem equation for a binary mixture under constant temperature and pressure is what? So we have derived this Gibbs-Duhem equation as this term. At constant, we are asked at constant uh, temperature and pressure. So at constant temperature and pressure, this TT terms are zero. So my equation I is equal to 1 to n, ni d mu I is equal to 0. So my equation can be n1 d mu 1 plus n2 d mu 2 will be equal to 0. So n1 d mu 1 plus n2 d mu 2 will be equal to 0. So this is my correct statement. Now let's move ahead with other part. Let's say I am dividing this equation both side by total n. So it will be n1 by n d mu 1 plus n2 by n d mu 2 plus n3 by n d mu 3 will be equal to 0, like that. And what is my n1 by n? N1 by n will be my mole fraction of particular component. So my equation will be x1 into d mu 1 plus x2 into d mu 2 plus so on will be equal to 0. So this second term is also correct. Okay, now let's try to write this equation in some other way. I have x1 into d mu 1 plus x2 into d mu 2 is equal to 0. So I can write it down as x1 into d mu 1 is equal to minus of x2 into d mu 2. Correct? So x1 into d mu 1 by dx1 will be equal to minus x2 d mu 2 by dx1. And my x1 plus x2 is equal to 1. So I can write it down dx1 is minus dx2. So I get this as x1 into d mu 1 by dx1 is equal to x2 into d mu 2 by dx2. So this is what my Gibbs-Duhem equation says in three different ways. First is n1 d mu 1 plus n2 d mu 2 is equal to 0. x1 d mu 1 plus x2 d mu 2 is equal to 0. And x1 d mu 1 by dx1 is equal to x2 del mu 2 by del x2. So all of these three options are correct. Okay. Okay, now let's move ahead. Assuming that ethylene gas obeys van der Waals equation of state. So van der Waals equation of state meaning it is following that P plus A by V square, V minus B is equal to RT, where V is my molar volume. Okay, so we are supposed to estimate the enthalpy departure function in kilojoules per mole for ethylene gas at 6.5 megapascal pressure and 30°C. And we are given the values of A as 453.046 into 10 raised to minus 3 into SI units, and B is 0.057 into 10 raised to minus 3 meter cube per mole in SI unit, and we are even given the molar volume as 1.1673 into 10 raised to minus 3 meter cube per mole. So let's first see if okay, this we are already told that this is van der Waals equation of state. So how did we derive it for van der Waals equation of state? We had this equation HR is equal to PV minus RT plus V infinite to V T del P del T at constant V minus P dV. Now for van der Waals equation of state, my del P del T at constant volume will be equal to R by V minus B. If I replace this R by V minus B in this equation, I get that my residual enthalpy is PV minus RT minus A divided by V. Okay, so I just need to put down the values. So let's say from whatever data that is given to us, that P is equal to what is our pressure of the system, 6.5 megapascal. So 6.5 into 10 raised to 6 Pascal is my pressure and temperature is 30°C. So T is equal to 30 in Celsius to Kelvin. I need to add 273.15. This is my temperature in Kelvin. And what do I need? I need PVRT. R will be my equal to 8.314 SI units. And what will be my volume? Volume is already given to us in the question. So my V will be equal to 1.1673, 1.1673 into 10 raised to minus 3 into 10 raised to minus. You can just write 1e minus 3, but I'm just writing for those who don't understand in MATLAB. So what will be my residual enthalpy? So HR is equal to, what is my equation? HR is equal to PV minus RT minus A by V. So I also need to define A and B. So let's define A and B. So my A is equal to 453.046, 453.046 into 10 is to minus 3, 10 is to minus 3 in SI units, and my B is equal to 0.057 into 10 raised to minus 3 in SI units. Okay, so what will be my H residual? So my H residual will be equal to first term P into V minus R into T minus A divided by V. So what is my residual enthalpy coming out to be very huge value? 4.6789 into 10 raised to 3. Let me check once again. PV minus RT minus E by V. So P into V minus R into T, yes, minus A by V. Okay, I need to find it in terms of kilojoules per mole. Okay, we are making some calculation mistake. Wait a minute. Is 10 is to minus, sorry, V is in 10 is to minus. Okay, yeah, here it is minus 4. I'm so sorry. Here V is minus 4. That's why we are not getting. Yeah, so this is into 10 is to 3. So if I divide whole equation, divide by 1000, so my answers will be in units of kilojoules per mole. So my residual enthalpy will be minus 5.6428 kilojoules per mole. Okay, minus 5.6 approximately. So what is this Z value if we calculate? So it is highly deviating from ideal gas. So my Z will be equal to P into V divided by R into T. So my Z is coming out to be 0.30. So it is highly non-ideal gas. Whatever this gas is, ethylene gas, I guess it is said. Yeah, ethylene. So this is not ideal gas because Z is coming out to be very, very far from unity 1. So that's why this is not an ideal gas. Okay, let's try to move ahead with another question. Estimate the entropy departure function in joules per mole Kelvin for ethylene gas at 6.5. Okay, same question, but we are supposed to find entropy departure function. So how to find entropy departure function? So for van der Waals equation of state, what was entropy departure function? It was nothing but R into ln of P into V minus B divided by RT. Okay, so let's try to plug this in. So Z is highly non-ideal, so it is not going to follow ideal gas law. So S residual is equal to, what is the equation? We derived it, right? We just put the value of del P by del T at constant volume as R divided by V minus B, and we find that that is nothing. SR is equal to R into ln of P into V minus B, ln of P V minus B by RT. Okay, so let's try to write down this equation. R into log of, it is log, not it is log, it is ln, not log 10 log of P into V minus B, this whole term divided by R into T. Okay, so see, it is coming out to be minus, I guess we have made again some mistake, P into V minus B divided by R into T. Yeah, I guess we have made some mistake. P into V, it is 10 is to minus, or P into V minus B, this numerator, divided by R minus T, divided by R into T, sorry. So it is coming out to be 15 minus 15.55. No, it is correct. Minus 15.55 kilojoules, 15.55 joules per mole Kelvin. Okay, here it should be kilojoule, not joule. I am sorry. So for kilojoules per mole Kelvin, we need to divide this value divide by 1000. Okay, so if I do this, so I get minus 0.0156. Okay, so this is how I can estimate residual properties. Let's say I'm looking at a value of temperature. No, but we cannot do it because our volume also varies with temperature, so we cannot do this. I had thought to do that. Let's try to vary pressure or temperature and see at what value we are getting z is equal to 1, but we cannot really do it because volume is already given to us in the question. Okay, so this volume is corresponding to this particular pressure temperature conditions. Okay. So let's move ahead. Cp minus Cv is equal to R. This is true for, okay. So from our second lecture, we had derived this very long theory. From here, what is Cp minus Cv? So we find that Cp minus Cv is minus T del P del V at constant temperature into del V del T whole square at constant pressure. Okay. So when my gas is behaving ideally, so my del P by del V at constant temperature, this term del P by del V at constant temperature will be equal to minus RT by V square. And del V by del T at constant pressure is R by P. So if I put this value minus T into this term into these terms square, so I get that Cp minus Cv is equal to R. So now we knew that Cp minus Cv is equal to R is true for only ideal gas. So when gas behaves ideally, so let's try to find it out when gas behaves ideally from this Z chart. Compressibility factor chart is here only in this chapter. Yeah, so see my Z versus P chart. So when my gas is behaving ideally, when my Z is equal to 1, Z is equal to 1 at very low pressures, and Z is equal to 1. Is it at low temperature? No. 200, 3, 225, 250, 300, 350. It is very high, 500 Kelvin. It is not exactly 1, but it is more or less near to 1. So what can we say that, what can we say when gas behaves ideally? Gas behaves ideally when we are dealing with low pressure condition and very high temperature conditions. So Cp minus Cv is equal to R is only valid for ideal gases, and gas behaves ideally at low pressure and high temperature. So our answer will be gas at low temperature and high pressure. Okay. Let's move ahead. Mu I. Mu I is the chemical potential of component I is equal to its molar Gibbs free energy Gi. What is it saying that mu I is equal to its molar Gibbs free energy Gi? Is it true for pure gas only, pure liquid only, pure solid only, or any component irrespective of its phase. So when we derive this equation, that this mu is equal to G. So here we are no way or no place we are saying that this is for liquid, this is for gas, or this is for anything. So this is true for all kind of system. This is true for all systems, pure gas also, pure liquid also, pure solid also. Any component, for any pure component, irrespective of its phase, mu I will be equal to its partial molar energy. We can check this. Sorry. You see, for any component, any pure component system, if we are at liquid phase or vapor phase or solid phase, it doesn't matter. This is true. Now, let's try to take one more problem. So that says that ammonia exists as a vapor liquid mixture at 321.55 Kelvin and 1.95 megapascal. Okay. So we are given that, sorry. So we are given that temperature is equal to 321.55 Kelvin and my pressure is equal to 1.95 1.95 into 10 raised to 6 pascals. Okay. My constants A is equal to 422.546 into 10 raised to minus 3 raised to minus 3 in SI units, and my B is equal to 0.037 into 10 raised to minus 3. Okay, these are my A and B values. Okay. Van der Waals equation of state, it is following. Estimate the molar volume of saturated vapor. Okay, so for any equation of state, when we have a look at PV diagram, so when we see from PV diagram that for solid and liquid, when I decrease the pressure or if I increase the pressure, volume change is very little. But when I'm going from liquid to vapor phase, so there is a significant volume change. So according to this line, this is my liquid route, this is my vapor route, and vapor volume will be very high compared to liquid volume. And there is one intermediate route that I have not drawn here, but yeah, this is my liquid volume. This is my vapor volume, and there will be one intermediate route that has no significance. Okay, so I'm supposed to find my vapor route. Okay, so what will be my equation? So my equation can be written as this V cube plus this B plus RT by P. Let's try to find out. Let's say my coefficient 1 is equal to my 1. So let's not worry about it. Let's write 1. Coefficient 2 is equal to minus B plus RT by P minus of B plus R into T divided by P. This will be my coefficient 2. My coefficient 3 will be equal to A by P. So my coefficient 3 is equal to A by P, and uh, my coefficient 4 is equal to minus A into B by P, minus A into B divided by P. So now to find this root, we can use zeros of coefficient 1, coefficient 2, coefficient 3 and coefficient 4. If I solve this, I have made some mistake. Sorry, not zeros, roots. Roots, sorry. Okay, let me roots. There is one MATLAB function in roots known as roots. Roots of any polynomial equation. So I just need to write down. Okay, it should be in this way. Okay, it is like this. Okay, let's say I'm defining this as my P. P is equal to this. And we don't need to give comma. And let's say I want to find my roots of P. Okay. So when I'm solving it, I have one root as 0.00 0.0012. Second root is negative. That doesn't make any sense. And third root is approximately coming out to be 0. Yeah. If I have a look at P, sorry, if I have a look at this P, so my first term is 1. So 1 into 10 raised to, uh, sorry, where did it go? Yeah, here, 1 into 10 raised to 1 into 0.0012. So my first root is 0.0012. Second root doesn't make any sense. And third root and fourth root are 0. So this means that liquid and vapor volume is very, very, very less. So liquid volume is very, very less. So this will be my vapor root, that is 0.0012. So that is equal to 1.24 into 10 raised to minus 3. It is 1.24. I don't want it to print like this, but okay. Okay, so this is what you get from here. Okay, 0 point, it is printing till this 4 digit only. 1, 2, 3. So, but we are still fine. 1.2 into 10 raised to minus 3 meter cube per mole. This is what we are getting. Okay, so this is all about our some demo questions. So what we have looked till now. So till now we started with first, second law of thermodynamics, why some particular processes are favorable and others are not favorable. Then we had a look at Maxwell relation, this spontaneity criteria, dH less than equal to 0, du less than equal to 0, ds greater than equal to 0, da less than equal to 0, and dg also less than equal to 0, in which Gibbs free energy is the most practical thing because it is at constant temperature and constant pressure. Okay. So from after that, we tried to find out ds values, dH, du for real gases. And when we try to find it with ideal gas, this particular terms goes to 0. So first we did all these calculations for real gas and then we moved to ideal gas. Then further we try to find out what is my Cp minus Cv values and Cp by Cv values. For ideal gas, Cp minus Cv is R and Cp by Cv is equal to gamma. So that is what we looked. Then so that gave us motivation to study the PVT behavior of any gases. So we tried to look at PV diagram and PT diagram. PV diagram tells that volume follows cubic equation of state. So among which two roots are significant. Volume, one is lower is liquid volume and higher is vapor volume. Okay. And after that, we looked at Peng-Robinson SRK RK equation of state. Then we had a look at Z value, Z compressibility factor way to find out PVT behavior of gases. Then we also looked at virial equation of state, one plus two ways, pressure explicit and volume explicit form, and we see that when we are dealing near to critical point, we need to 3 till third coefficient. Okay, so this is what we studied till last class, and in today's class, uh, also we studied in last class 2 parameter and 3 parameter corresponding state theory, and in today's class, we continued it and we looked at what is residual properties for these real gases. First, using equation of state approach, we try to find the equation, and then we try to have a look at Van der Waals equation of state, what is residual enthalpy and residual entropy values. Then from there, we move to Z values, how to find that using compressibility factor chart. So for that we need Lee-Kesler charts for HR by RTC, HR by RTC for ideal and ideal part and this deviated part. Further, we try to do the same thing for virial equation of state. Now after that we try to find out what is we looked at everything till here as closed system. Then we try to move from closed system to single component open system, where we added mu into dn term, and very important term, we know that mu is equal to g only equal to del g by del n at t comma p. For other thing, del u del n at s comma v is not equal to small u. So that is what we learned. And for multi-component system, we added this summation of mu I dni term. And further, we had a look at Gibbs-Duhem equation, very, very, very important thermodynamic concept, that we cannot vary Tp and mu all at same time. If we are fixing T and P, mu is automatically getting fixed. So, and this is what we learned in today's class. Okay, so thank you so much. And if anyone has any query, you can write to me on this particular email ID. I will try to respond to your query as soon as I can. Okay, so thank you so much, and we will meet again next week.